Welcome to the semi-learned lecture on how negative feedback works and how it turns the unassuming op-amps into useful amplifiers. At the outset, let's confirm why we are here. We may have just finished watching our previous video on how to solve op-amp exam problems and are now motivated to understand how negative feedback creates working amplifiers. Or we may have heard of how negative feedback impacts all aspects of our lives, and we want to learn a little bit more about it. Indeed, we are surrounded by systems that depend on negative feedback to be viable. Our bodies use negative feedback to regulate everything from our heart rate to the level of glucose in our body. Negative feedback ensures that the internal traffic of the internet flows uninterrupted, that motors do not go crazy and spin out of control, that airplanes maintain their altitude, that electrical power is generated safely, and that large language models and other AI constructs are trained in a reasonable amount of time. It is even used by central bankers to try and stabilize the economy of countries and the world. So it's worth understanding how negative feedback works, no matter what field one practices. To explore negative feedback, we will adopt amplifiers as our example of a system that needs negative feedback to operate effectively. Amplifiers are simple electronic circuits that take in a very faint input electrical signal and, like the triangle wave that we see here, amplify it to produce a much larger output signal. The word amplifier may remind us of the volume knob on the ancient radios and receivers, or those annoying megaphones. But we also needed them when we used landline phones, and we also used them to detect faint electrical signals in medical equipment. Then they became really handy when the wireless revolution occurred, where they amplified Wi-Fi and cellular signals for us. Not to mention that we use them whenever we listen to our music, podcast, and occasionally phone calls, especially when we are using our wireless Bluetooth headset. And there are two simple rules that any amplifier must follow. Rule number 1 is that the output signal must be identical in shape to the input signal. Rule number 2 is that the output signal should be larger in magnitude compared to the input signal. So the shape of the output waveform remains a triangular, just a much larger triangle when compared to the input signal. To amplify the faint input signal, the amplifier requires electrical power, which we supply to it using two fixed level voltages, the positive supply voltage Vs plus and the negative supply voltage Vs minus. Almost all modern amplifiers are built using a fundamental electronic component called the operational amplifier, or op-amp for short. And this is the diagram of the basic op-amp. Upon seeing this diagram, most people are surprised to discover that instead of having a single input for attaching the faint input signal, the op-amp actually has two inputs. They are both called V sub I, implying that they are inputs, but the plus and minus signs attached to each of them implies that we need a positive and a negative signal as input to the amplifier. This begs the question of how should we connect the single incoming faint input signal to the two input ports of the op-amp. To answer this question, we must first delve a little bit inside the op-amp to understand how it works. Operational amplifiers are designed to amplify the difference between two different signals. When two different signals are applied to its two input terminals, the op-amp will first subtract the signal that appears on the negative input terminal from the signal that appears on the positive input terminal, and then it will amplify the difference between these two signals. In textbooks and in lectures, the negative input terminal is often called the inverting terminal, while the positive input terminal is called the non-inverting terminal. But we prefer to refer to them as the negative and positive input terminals to better match the V input minus and V input plus symbols that are often used in op-amp circuit diagrams. The designer of op-amps intentionally chose to amplify the difference between the two inputs, instead of just amplifying a single input signal. And that was chosen because it enables negative feedback, as it will become apparent to us in the next few minutes. But for now, let's think about how do we connect the faint input signal to the two inputs of the op-amp. What if we connected the faint input signal to the positive input terminal of the op-amp and simultaneously tie the negative input terminal to ground, which always has a voltage of 0? With the ground always being at 0 volts, the faint input signal will not be modified by the subtraction and will show up unaltered at the output of the subtractor. The resulting signal, which is identical to our input faint signal, is ready to be amplified. Amplification is equivalent to multiplying the signal after the subtraction by a gain factor to produce the output signal. Okay, this seems like a very plausible approach to using the op-amp as an amplifier for the input signal. But when we look at the usual values of the gain factor, we immediately find a problem that would upset this plausible approach. So what would be a typical value for the gain factor of an op-amp? One would think that the gain factor in the order of 10, 100, or even 1,000 would be sufficient. This way, if the peak-to-peak amplitude of our input signal was a tiny 2 millivolts, then a very decent amplification factor of about 1,000 will boost it to a respectable peak-to-peak range of 2 volts. But instead of making the gain reasonable, like 1,000, engineers usually design op-amps with massive gain factors, like 100,000, and often even more than that. For now, let's ignore the question of why the op-amp gain is so high, and instead focus on what would happen if our 2 millivolt signal was to encounter such a high gain of 100,000. Well, 2 millivolts times 100,000 would theoretically give us a signal whose peak-to-peak amplitude is 200 volts. That is a massive output voltage, and it would be due to a very small 2 millivolt input. And if the input was a more respectable 20 millivolts, then the theoretical amplitude of the output signal would be a very dangerous 2000 volts. Of course, all these are just theoretical calculations. In reality, the maximum output of the op-amp can never exceed the supply voltages that we provide to run the op-amp's internal circuits. These positive and negative supply voltages are usually about plus 15 volts and minus 15 volts respectively. So the maximum voltage that an op-amp can produce is just a tad less than 15 volts in the positive side and a tad above minus 15 volts on the negative side. So, how will these finite supply voltages impact the shape of the output signal? Assuming that the typical gain of a modern op-amp is around 100,000, then theoretically the output signal would go to a peak-to-peak voltage of 200 volts. But in reality, such a huge output will never be produced by an op-amp which is powered only by plus and minus 15 volts. Instead, whenever the input signal times the gain results in a number that is within the range of plus 15 to minus 15 volts, then the op-amp will produce a nicely amplified version of that part of the signal. However, once the value of the input signal times the gain results in a number that is larger than plus 15 volts, then the op-amp can only produce a voltage that is just below 15 volts. And the same thing will happen if the input voltage times the gain results in a number that is lower than minus 15 volts. In that case, the op-amp will just produce an output value that is very near to minus 15 volts. We now see that the output signal is going to be clipped, and yes, that is a technical term, at plus and minus 15 volts. Therefore, this configuration of the op-amp, coupled with a very high gain, will break the first and most important rule of amplifiers, which stipulates that the output signal has to have the exact shape as the input signal. Clearly, we need a new arrangement for connecting the input signal of the to the op-amp and have a result that is a proper amplification. Let's try another way to connect the faint input signal to the op-amp that would hopefully not produce clipping. We will now rely on the fact that the op-amp amplifies the difference between the two terminals. Think about what would happen if we created a new configuration that does not have the ground connection to the negative input terminal. Instead, what if we connected another signal that looks just like the faint input signal, but whose amplitude was just a tiny bit smaller than the input signal. For example, let's assume that the new signal is exactly the same faint input signal multiplied by 0.9999. That's 4 nines. In that case, the difference between the two signals would have the same shape as the input faint signal, but be of extremely small amplitude. Actually, it would be 10,000 times smaller than the input faint signal. Now, if we multiply the difference signal, by the massive gain of the op-amp, it's going to result in an output that's only 10 times the amplitude of the original faint signal. Great! We've just figured out a potential way to amplify our input signal without clipping it. All we have to do now is generate that slightly smaller input signal in a very reliable manner. Luckily for us, a very reliable method for generating the small signal was devised in 1927 by Harold Black, an engineer who was solving the clipping problem for amplifiers that used to be made out of vacuum tubes instead of op-amps. His solution to the problem was to invent the concept of negative feedback, and so negative feedback is what we are going to look at right now. Harold Black realized that if the amplifier did not clip the output signal, then the output signal is going to have the same shape as the input signal. Therefore, we can use the output as a source for that slightly attenuated signal that we will connect to the op-amp's negative input terminal. All we have to do is connect the output signal through a feedback circuit that reduces the amplitude by a fixed amount, and then connect the output of the feedback circuit to the negative terminal of the op-amp. This type of feedback is called negative feedback because the output of the amplifier is connected to the negative input of the op-amp. More importantly, it is subtracted from the input faint wave that appears on the positive input of the op-amp. It is this process of subtracting the feedback signal that makes the system a negative feedback configuration. Now, of course, this simple concept assumes that the output wave appears on the amplifier's output almost instantaneously when an input signal is applied to the positive terminal. Luckily for us, electronic amplifiers have an almost zero propagation time from the input to the output, and so the shape of the output signal is almost instantaneously a replica of the input signal. The simplest form of a feedback circuit is just a zero resistance wire that conveys the output voltage directly to the negative terminal. A wire with zero resistance is an electrical short circuit. But what amplification do we get from this very simple circuit? There is a mathematical way of answering this question, and there's also a very intuitive, qualitative way of understanding it. We are going to explore both approaches, starting with the intuitive approach first. To understand how the negative feedback works on an intuitive level, we must first get acquainted with the op-amp's input versus output curve, which we will draw on this graph. On the x-axis, we represent the result of subtracting the two input voltages, and peeking inside the op-amp, we see that the x-axis captures the voltage at an internal point in the op-amp right after the subtraction happens. So, if the positive input has a higher voltage than the negative input, we're going to be on the positive side of the x-axis, and vice versa. The y-axis is much simpler. It's just the voltage output of the op-amp, and the voltage output is generally called V sub out or V sub O. Now, because of the ridiculously high gain of the op-amp, any significant difference between the two input voltages will result in a theoretical output voltage that is well beyond the supply voltages of the op-amp. And knowing that the op-amp can never produce a voltage beyond its supply voltage, then for each of these points, for each of these cases, the op-amp will just produce an output that's approximately equal to the positive supply voltage, which is Vs plus. Now we notice that because of the massive gain of the op-amp, this situation occurs for almost all values on the x-axis. It also means that the op-amp will produce an output that's approximately equal to the negative supply voltage, or Vs minus, for almost all values that are negative on the x-axis. Now we call these two regions of operation the saturation regions because the value of the x-axis does not change the op-amp output during these two regions. The op-amp is actually useless in these regions because its output does not change in response to a change in the input. Now, all of this leaves us with a very, very small region where the difference between the two input terminals is so small that when that small difference is multiplied by a massive op-amp gain, the resulting number is still within the range of the supply voltages of the op-amp. And for that tiny region, we have a proportional relationship between the difference of the two input signals and the output voltage. That proportionality relationship is expressed by this very steep line that goes through the origin, and this line represents the region where the op-amp can be useful to us by doing proportional amplification. The slope of that line, which we are going to define as a constant value, g, is the value of the op-amp's gain factor. And so we can formulate this very simple straight line equation that describes the relationship between our x and y variables. And because this amplification region is well described by a straight line, we usually call it the linear region of the op-amp. Now let's think about the width of that linear region on the x-axis. It is extremely narrow, and yet that is the region that we will need the op-amp to operate within so that the output is not clipped by the limitations of the supply voltages. To illustrate the narrowness of the linear region on the x-axis, let's continue with our typical op-amp that has a gain of 100,000 and is supplied by plus 15 and minus 15 volts, which would be the output voltages when the op-amp operates in the useless saturation regions. To find the width of the linear region on the x-axis, we want to find the x-axis values for the 2 points highlighted by the red circles. To do that, we can just set the value of the output voltage in the linear region equation to be equal to the supply voltage, and we solve for the value of the x-axis that would produce such an output voltage. When we plug in the values of the gain and the supply voltages into the linear region equation, we find that the linear region would start at an x-axis value of minus 0.15 millivolt and will end at an x-axis value of 0.15 millivolt. Now that is a grand total for the range of the linear region on the x-axis of 0.3 millivolt from start to end, and that is ridiculously small. For example, a typical Wi-Fi signal or FM radio signal will produce well over 1 millivolt of strength in the receiving antenna. And that's already well beyond the range of the op-amp linear region, and therefore beyond what this op-amp can amplify without clipping. And yet, if we want to use the op-amp as an amplifier, we must keep the difference between the two inputs within that very narrow range so that the output voltage remains proportional to the input voltages. The problem, of course, is that we have no control whatsoever on the value of the faint input signal. It may easily go beyond this very narrow range. That is where negative feedback becomes so important in producing the second signal, which we are going to attach to the negative input terminal and subtract it from the faint input signal to produce a difference signal that continues to be small enough that it lies within the range of the linear region. To explore how the negative feedback keeps the op-amp in the linear region, let's go back to our first amplifier configuration, the one that didn't work so well. And let's put 0 volts on the positive input terminal of the op-amp. Now, observing that the negative terminal is connected to ground, which is also 0 volts, then the difference between the two terminals will be 0, and the output has to be 0 also. Now let's remove that ground connection and very quickly insert the negative feedback short circuit between the output and the negative terminal. The output was previously at 0 volts, and since the short circuit feedback conveys that same value to the input, then the input to the negative terminal will remain at 0 volts. And with both inputs at 0 volts, the difference between them remains at 0, and even if the value of the gain is extremely high, the output voltage stays at 0 volts. If we were to place the operating point of this entire system on the input-output curve of the op-amp, then we would have 0 for the x-coordinate and also 0 for the y-coordinate, which would place us exactly at the origin of the input-output curve, as denoted by the green cross here. Negative feedback continues to convey the output voltage back to the negative input terminal, which keeps the amplifier stable at this state, with the output producing the same value that we applied on the positive terminal of the op-amp. Also notice that the feedback has placed the op-amp in the linear region. Now let's see what happens when we start to increase the input voltage on the positive input terminal. Starting with our previous condition, let's now start to raise the voltage on the positive terminal from 0 volts towards a very modest 1 millivolt, and let's see how the system reacts. Naturally, a rising voltage on the positive input will cause the output voltage Vout to start rising from 0 to a new higher level. Eventually, it's going to settle at a new value that is proportional to the difference between the two input terminals. But what is the difference in the voltage between the two input terminals? The negative feedback connection will make the negative input equal to the value of the output voltage. So as the output voltage rises, the voltage on the negative input terminal will also rise. That rising voltage on the negative input terminal means that the difference in voltage between the two input terminals gets smaller as the output voltage increases. This puts a limit on how high the output voltage can go up. And that is how negative feedback works. The output voltage is not going to rise to a very, very high value because as the output voltage increases, negative feedback kicks in and limits its final value. The question now becomes, at what value will this V output settle? Would it be much higher than the 1 millivolt, or will it be somewhere closer? Now we can find out the exact end value of the output voltage by solving two simultaneous equations that describe the behavior of this negative feedback system. The first one is the feedback equation. That is that the voltage on the negative input is really equal to the output voltage. The second equation is the one that describes the input-output relationship of the op-amp. But this op-amp equation is problematic because we do not know what region the op-amp is operating in. Will it be in the linear region or the saturation region? In order to figure out the region in which the op-amp works, let's do a thought experiment. We start from the previous state where the positive input terminal was set to 0 volts and the output and negative input terminals were correspondingly at the same level. In that state, the operating point of the op-amp was at the origin of the input-output curve. And due to the feedback short-circuit connection between the input terminal and the output voltage, we can and we must update the label of the x-axis to reflect this relationship. This is very important, and we're going to see why very shortly. We are now ready for the input to rise from 0 volts to 1 millivolt. This causes the difference between the input and output voltages to become 1 millivolt, which we plot as the star on the x-axis. That 1 millivolt is well beyond the linear region of the op-amp, and based on the input-output curve, it implies that the target end value of the output voltage will be within the saturation region, which means that it's going to be near 15 volts. And so the output voltage will start to rise towards that 15 volts. At that point, the magic of negative feedback will come into full view. For as the output voltage rises, the short circuit forming the negative feedback conveys that value back to the negative input terminal. That means that the difference between the positive input and the negative input has now decreased significantly, moving the x-axis point much closer to the origin. That is why we changed the label on the axis to show that it has now become dependent on the value of the output voltage. The updated x-axis value will move the target output voltage to the corresponding value on the input-output curve. This upward motion in the output voltage and then the corresponding downward motion of the target voltage will continue until an equilibrium is achieved, where the output voltage and the target voltages are equal. Now notice that we've shown that the equilibrium will happen somewhere in the linear region of the input-output curve. Is that what really is going to happen? To ascertain in which region the op-amp will operate, let's zoom in near the origin of the curve to see how much Vout will have to move away from 0 volts for the system to reach equilibrium. At the start, the difference between the output and the input is 1 millivolt, which, when multiplied by the gain, which is 100,000, will give us a target voltage of 100 volts. Now 100 volts is well beyond the supply voltage, and so the target for the output will just be the supply voltage. Now if in response to that 1 millivolt input voltage, the output voltage starts to move up a tiny amount from 0 volts to 0.9999 millivolts, that's 4 nines, then the difference between the input and the output voltage will become 0.0001 millivolts. That small change in the y-axis has resulted in a massive change in the x-axis from 1 millivolt to 1,000 times less what it was. The target voltage will therefore also drop from the supply voltage to just 10 millivolts. This new target will keep the output voltage moving higher, but towards a much smaller target. Let's assume that it moves up by a minute amount to just 0.99999 millivolts. That's 5 nines. The difference has now become even smaller. It's become 0.00001 millivolts. And that gives us a new target of 1 millivolt. With that new target of 1 millivolt, the difference between the input and output voltage gets even smaller. Now the output voltage will keep rising, but by a smaller and smaller amount. And if we continue iterating, we are going to find that it converges at a voltage that is just below the input voltage of 1 millivolt. This converging behavior is due to the behavior of the negative feedback and the presence of the very high gain. But most importantly, the combined power of negative feedback and the high gain has resulted in the value of the output voltage that makes the value between the positive and negative input terminals much, much smaller than the span of the linear region, which we had calculated to be about 0.3 millivolts for a typical op-amp that has a plus minus 15 supply voltage and a 100,000 gain factor. In other words, the negative feedback and the large operational amplifier gain ensures that the op-amp operates in the linear region at all time for this negative feedback system. Now at this point, some of us may be incredulous. We have only conducted one thought experiment, and yet we're jumping to the conclusion that having this negative feedback connection with the very high gain of the op-amp will result in that V output, and therefore V input minus, will be moving to be very close to the input voltage, which then ensures that the op-amp is always operating in the linear region. And yet, that is exactly what is going to happen no matter what value of voltage we place on the positive input terminal. Each of us can go off and try it out for ourselves. We will see that for any input voltage, no matter positive or negative in value, and no matter if it is small or large, as long as it's within the range of the supply voltages, the negative feedback will force the op-amp to subtract the existing output voltage value from the newly applied input voltage. That subtraction will set a trajectory for V out in the direction of the newly applied input voltage. And once the output voltage starts approaching the value of the input voltage, the result of multiplying the difference by a very large gain forces the output voltage to converge to a value that is very close to the voltage that we placed on the positive input terminal. In fact, that very large gain forces the difference between the input and output voltages to become a small fraction of a millivolt for typical op-amps. Such a small value keeps the op-amp in the linear region all the time. We really should try this out for ourselves. We can use plus 4 volts or minus 8 volts or even 12 volts. No matter what voltage we try, we will find that the output voltage will pretty much track the voltage that we place on the positive input terminal. And through the short circuit feedback path, the voltage on the negative input terminal will also track the voltage that we placed on the positive input terminal. Now, whenever two circuit nodes exhibit the same voltage, it must be because they are connected via a zero resistance wire that forms a short circuit. And we have just seen that the feedback and the high gain causes the negative input terminal to closely track the voltage on the positive input terminal. And yet, having understood how op-amps work, we all know that there is no zero resistance wire connecting the two input terminals of the op-amp. Instead, the magical behavior of negative feedback ensures that the negative input terminal tracks the voltage that we placed on the positive input terminal. This non-physical short circuit effect is called the virtual short circuit, And this virtual short circuit equation in the yellow box is therefore used whenever negative feedback and high gain exists in a complex op-amp problem. We demonstrated this in our previous video on how to solve op-amp exam problems, and this QR code can lead you to the video in case you are interested. Although the thought experiment already showed us that the output voltage will closely track the input voltage, we do not have an exact equation for that relationship. But now that we know that the op-amp is in the linear region, we can use the op-amp linear region equation as well as the feedback equation to get such a relationship. Now, substituting the feedback equation to eliminate the negative input terminal term inside the op-amp linear region equation, we will solve for V out as a function of the input voltage, and then we will get this very simple equation. This equation tells us that as long as the gain factor is positive, which it always is in op-amps, the output voltage will always be just a tiny fraction lower than the input voltage. Now we can validate this by plugging in a typical gain of 100,000 into the equation to see how close the output voltage is to the input voltage. And to me, the value looks very close to 1. This confirms our thought experiment result that the output voltage will be very close to the value of the input voltage. And because of the negative feedback equation, the voltage on the negative input terminal will also be very close to the input voltage. If you recall earlier in this video, we wanted to create on the negative input terminal a new version of the faint signal that is just a fraction smaller than the signal on the positive input terminal, so that we would not get any clipping on the amplifier output. And from this last equation, it seems that we have accomplished this goal on the negative input terminal through the use of negative feedback. But all this leaves us somewhat unsatisfied. For all the work that we did not get any amplification of the input voltage. The output voltage will just closely follow the value of the input voltage. And that is why this configuration is called the voltage follower. In practical electronics, there are many situations where such a configuration of the op-amp is very useful. It is useful to isolate two circuits from each other, but for now, we are still confronted with the problem that our first amplifier does not seem to amplify the input signal. To get to an amplifier that actually amplifies, we're going to start with this voltage follower configuration. It turns out that there are two effects preventing this voltage follower configuration from amplifying the input voltage. The first effect is due to the very large gain of the op-amp, which when coupled with the negative feedback, keeps the voltage on the negative input terminal approximately the same as the voltage on the positive input terminal. This is the effect that's referred to as the virtual short circuit between the two input terminals, even though no physical short circuit exists. And it's a good effect because it prevents the output signal from being clipped. The second effect is due to the nature of the feedback circuit that we created. By putting in a real, actual, honest-to-goodness physical short circuit between the output and the negative input terminal, we forced V out to be exactly the same as the voltage on the negative input terminal. That is the main reason why V out cannot move far from the value of the voltage we placed on the positive input terminal. Looking at the problem from this perspective, the path to amplification seems easy, for we still want the large gain and the feedback network so that we can continue to benefit from the virtual short circuit effect that prevents the output voltage from being clipped. We just want a different feedback circuit that allows V out to be higher than the voltage on the input terminal in order to get some amplification to occur. We therefore need to replace the short circuit wire between V out and the negative input terminal of the op-amp with another circuit element that would allow these two nodes to have different voltages. The most obvious element would be a resistor. If we connect a resistor between the output and the negative input terminal, and if we allow a current I to flow between them, then there will be a voltage drop proportional to the value of the resistor R. Okay, problem solved. We just place a resistor instead of a short circuit in the feedback path, and we should get amplification because the resistor will allow V out to have a higher voltage compared to the negative input terminal. And at the same time, the resistor will be providing a negative feedback path for us so that we can maintain the benefit of that all-important virtual short circuit. So now we place the resistor in the negative path of the op amp. We still expect to get the same benefits of the high gain and the negative feedback effect, which will keep the voltage of the two input terminals really close to each other. That means that the op amp was going to remain in the linear region, and we get to keep using the linear region equation for the op amp. But for the feedback network, we can now use Ohm's law to describe the voltage drop between Vout and the negative input terminal. Unfortunately, we quickly run into a problem that pertains to the electrical characteristics of op amps. For all op amps are designed so that their input resistance is extremely high, so high that we can consider it infinite. Now, so far, we have been drawing the op amp from a functional perspective, but if we draw it from an electrical perspective, then we focus on the input pins and we see that the input terminals appear to be connected to ground via internal resistors that have infinite resistance and which we denote by the symbol R sub infinity. Now do not be alarmed because this new diagram may be different than other electrical diagrams that you have seen in books or lectures. Most books and lectures use diagrams that mimic the behavior of the op amp when subjected to very small alternating voltages, and that's an advanced topic for folks attending 3rd or 4th year university electronic courses. For a basic understanding of how the op amps work when the input signal is a constant voltage, this representation that we are looking at is more suitable and easier to understand. These infinite resistors were the second magic property of op amps that we used in the previous video to solve many op amp problems, and which you can view by following the link on that QR code. What we should be alarmed about in this new diagram is that the input resistance is infinite, because that has grave implications on our feedback equation. The infinite input resistor of the op amp means that no current could flow through them, and therefore the current through the feedback resistor is going to be zero. That means there will be no voltage drop between Vout and the negative input terminal, and that the right hand side of the feedback equation is now going to be equal to 0, which takes us back to the voltage follower configuration, where no amplification happens because the voltage at the input terminal is the same as that on the output. Now, this may be a bit frustrating, but there's very good reasons behind why the chip designers create op amps with infinite input resistances. But for now, we just have to work around this inconvenience so that we can get the op amp configuration to amplify. We want current to flow across the resistor R so that there will be a difference in voltage between Vout and the negative input terminal. We think this is going to give us some amplification, but the infinite input resistance of the op amp is getting in our way. Now, one way to solve this problem would be to add a finite resistor in parallel with the infinite input resistor of the op amp. For example, we can add a second external resistor outside the op amp between the negative input terminal and ground. If we look carefully at this new resistor, it is indeed in parallel with the infinite internal input resistance of the op amp because it is connected to the same two terminals, ground and the negative input of the op amp. We'll call this new resistor RG for ground, and for consistency, let's rename the feedback resistor as RF instead of just R. Now we're going to have current that originates from the output terminal of the op amp and runs through RF, then continues through RG into the ground connection. But of course, there will be no current entering the op amp because it has infinite input resistance. Great. Now we actually have a voltage drop between the output and the negative input terminals, which means that we can use the two simple equations that we talked about last slide to evaluate the amount of amplification. We just need to add a third equation that describes the value of the current. That would be Ohm's law, describing the current flowing due to the output voltage being dropped across RF and RG. Notice how the current I is solely dependent on the value of the external resistors and the output voltage. We now face two paths that will both lead us to a relationship between V output and the input voltage for this amplifier configuration. We will start with the more difficult path, the one that we would never use to solve op-amp problems in exams and quizzes, but it does provide some insights, and we urge you to try this out the harder way before we reveal the easy way. The harder way proceeds by solving three simultaneous equations to obtain the relationship between the input and the output voltage. First, we apply the current equation into the feedback equation, and then next we apply the resulting feedback equation into the op-amp linear region equation. And as we are doing this, we are going to use a simple hint. Whenever the term Vout divided by the gain appears in our solution, we can reason that the voltage is always going to be less than the supply voltages, which is around 15 volts, and that the gain will always be very high, like 100,000, and so that term can be assumed to be approximately zero. Solving the equations is very basic algebra and should only take a few minutes. We can even pause here for all of us to solve the equations by hand. Once the algebra is completed, the solution should look like this. That formula tells us that Vout can now be much higher than the input voltage. The amplification factor, which is shown in red, is proportional to the ratio of the two of the resistors. So if we set RF to be 100 times larger than RG, then the amplification factor will be about 100. Actually, it'll be about 101 because of the number 1 in the equation. Happily for us, when it comes to op-amp problems, as well as in real-life amplifier design, we never solve op-amp problems by solving the three simultaneous equations like we just did. There is much simpler paths to solving the op-amp problem. It uses the knowledge embodied in the feedback and op-amp equations, but without really using the details of these two equations. Let's explore that simpler way right now. The two equations that represent the op-amp behavior and the feedback network are just mathematical representations of how the very high gain and the negative feedback impact the relationship between the two input terminals. We already know from our thought experiments and also from the voltage follower equation that these two effects force the voltage on the negative input terminal to get extremely close to the voltage that is applied to the input positive terminal. This is the famous virtual short circuit equation. So we can replace these two equations with one simple equation that summarizes their net effect. That is that the voltage on the negative input terminal is almost the same as the voltage on the positive input terminal. So now we no longer need to consider these two equations, and instead we just use the virtual short circuit equation that combines these two equations. Now let's see how easy op-amp problems become when we use the simplified equation. If we can relate the output voltage to the voltage on the negative input node, then the virtual short circuit equation tells us that this is exactly the same relationship between the output voltage and the voltage we apply to the positive input node. Luckily for us, the output voltage and the voltage of the negative input terminal are easily described by the resistive voltage divider of two resistors. Here's the simple voltage divider equation. And because of the op-amp's gain and negative feedback, the voltage on the positive input terminal is equal to the voltage on the negative input terminal. If we just keep the input and output voltages and rearrange the equations, we are going to get this formula. This is exactly the same formula that we obtained just a few minutes ago by solving three simultaneous equations. So why should we ever solve op-amp problems with anything other than the simplified virtual short circuit equation? This is exactly the method that we described in our previous video on how to solve op-amp problems for exams and quizzes. And here is the QR code again in case you want to get to that video. Now before we move on, let's examine some important attributes of this amplifier that we've just created. The amplifying op-amp configuration we just created is called the non-inverting amplifier. Not only does it amplify, it also does not invert the polarity of the input. This means that if we place a positive voltage on the positive input terminal, then the resulting output voltage will be an amplified voltage that is also a positive voltage. We can see this from the equation that describes the input-output relationship. The amplification factor is always positive, and so the output voltage will have the same polarity as the input voltage. It follows that if we place a negative voltage on the positive input terminal, then the resulting output voltage will be an amplified voltage that is also a negative voltage. Now in a few more slides we will encounter the inverting amplifier that reverses the polarity of the input voltage when producing an output voltage. But before we do that, there are still a few more things to discuss about the non-inverting amplifier. At this point, some of us may be wondering whether the addition of resistors changed the beneficial impact of negative feedback and high gain. Will we continue to get a virtual short circuit between the two input terminals of this new amplifier configuration? The answer comes from the simple thought experiments that led us to the virtual short circuit conclusion in the first place. Because the op-amp gain is so high, any time the voltage at the negative input terminal gets far away from the voltage that we placed on the input terminal, the feedback mechanism will force it back towards the input voltage that we placed. The same principles we used in the voltage follower configuration will apply here. If any of us still have any doubts about the effectiveness of the thought experiment, we can always solve the three simultaneous equations again, but this time we can derive a relationship between the voltages on the two input terminals. When we solve the three equations, we get a new formula, which confirms that the virtual short circuit relationship holds for the non-inverting amplifier as long as the op-amp gain is very high, like 100,000. High op-amp gain and negative feedback are very powerful and useful concepts. So we now understand one of the key benefits of high gain in op-amps. It ensures that the op-amp stays in the linear region when we apply negative feedback. We are now ready to understand a second reason for why designers make op-amps with very high gain. Most users of amplifiers need an amplification ratio in the range of 10 to 1,000 times the input signal. The key word here is range. Different products require different amplification ratios, but creating an op-amp for every type of electronic product is not desirable from a financial perspective. Makers of op-amps want to make one device that gets used in all electronic products that each have different amplification needs. They want to create a single op-amp that has a fixed gain factor and then have a method that adjusts the gain to whatever value is needed. Such adjustments should be done using cheap components like resistors, which, when attached to the external terminal of the op-amp, would produce an amplifier whose gain is proportional to the value of these resistors. If the gain of the amplifier is proportional only to the value of the resistors, end users will have full control of the resulting amplifier gain. And we have just seen exactly that concept through the amplification equation of the non-inverting amplifier. And here are two examples of this concept. Because the value of the op-amp internal gain was designed to be so high, the gain of the overall amplifier ended up being fully controlled by the values of these two resistors. Moreover, we were able to select the values of these two resistors in a way that resulted in a reasonable amplification factor of 11 or 26. Such reasonable amplification factors would not cause the output waveform to be clipped. Incidentally, there is a third practical reason why op-amp builders choose to build op-amps with very high gain, and we're going to address that reason in a future presentation about how to build an op-amp. Returning to the topic of amplifier configurations, there exists a third amplifier structure that we must learn. It is called the inverting op-amp amplifier, and it looks like this. It's a bit different from the non-inverting amplifier, but let's not be alarmed. We have all the knowledge needed to understand how this amplifier works and also how to derive the amplification equation for it. Let's take things one step at a time. First, in the diagram, we flip the locations of the positive and negative input terminals to make the diagram more readable, but they still perform the same functions as we learned before. Secondly, we have tied the positive terminal to ground, so the input voltage cannot be coming through that terminal. Instead, the input voltage that we need to amplify is now denoted by V sub I and seems to be connected to the negative input terminal of the op-amp through the resistor Ri. No worries, we will soon handle that. The key thing that we need to check is whether there is a negative feedback network in the circuit. That would be a connection between the output of the op-amp and the negative input terminal. Is there such a negative feedback? Indeed, it is, as shown here with the dotted red line. That is good news, because when we have negative feedback network, and assuming that the op-amp has a very high gain, which it always does, then these two factors will work together to create the virtual short circuit condition between the two inputs. In other words, the voltage on the two terminals is going to be approximately, the two input terminals is going to be approximately the same. This is the virtual short circuit that we saw before, and because we tied the positive input terminal to ground, which is 0 volts, then the negative feedback and the high gain will keep the voltage on the negative input terminal of the op amp at about 0 volts at the same time all the time. We now know enough to create the amplification equation. Because the voltage at the negative input terminal is 0, then there will be a current flowing from the input voltage Vi to that 0 voltage through the resistance Ri. Using Ohm's law, we can get the value of that current I sub I. So where would that current flow to? Well, it cannot go into the op amp because the op amp has almost infinite input resistance. So the only other way it can go is through the resistor Rf. Let's call that current going through the resistor Rf I sub F. Applying Kirchhoff's current law at the op amp negative input terminal, the two currents I sub F and I sub I must be equal. We can also find the formula for I sub F using Ohm's law between the 0 volts at the negative input terminal and the voltage at the output terminal. Now, if we take Kirchhoff's current law and substitute the equations for I sub I and I sub F into it, we will get a relationship between the input and output voltages. Rearranging a little bit, we get this relationship between the input and output voltages, where the amplification factor is shown as Rf over Ri. So setting Rf to be 10 times higher than the resistance of Ri would give us a 10 times amplification factor of the input voltage. But what is that negative sign in the equation? What does it mean? The negative sign in the amplification equation for this amplifier is what gives it its name, inverting. The negative sign tells us that if the input voltage was a positive voltage, then the output voltage is going to be a negative voltage. It will be amplified, but negative. Alternatively, if the input voltage was a negative voltage, then the output voltage will be positive. And all of this kind of makes sense. Previously, for the non-inverting amplifier, the input was connected to the positive input terminal of the op amp, and so the result was not inverted. Whereas here, the inverting amplifier, the input is connected to the negative input terminal, and so the output is inverted. It also makes sense when you look at the voltage on the positive input terminal. We have tied that voltage to ground, and because of the combined effect of the negative feedback and the high op amp gain, the negative input terminal of the op amp will also always have a 0 volt on it. If the input voltage was positive, then the current I sub I would have to flow from the left to the right, as we are shown here. And because of Kirchhoff's current law, I sub F has also to flow from the left to the right. Given that the voltage at the negative input terminal of the op amp is 0 because of the virtual short circuit, then V out will have to be a negative voltage for I sub F to flow in the direction that we've shown here. So all of this makes sense, but it does pose an important question. What path does I sub F take as it exits the resistance R sub F? The only path it has is to go into the op amp. Is that possible? And what does that tell us about the behavior of the output terminal of the op amp? We previously looked at the electrical characteristics of the input terminal of the op amps and said that each of them are best represented from an electrical perspective as an infinite resistor. What about the electrical characteristic of the output terminal? Well, we know that the op amp produces a voltage V out as its output. Now that voltage can either be a fixed value near the supply voltage if the op amp is in the saturation region, or it can be a linear function in the linear region. But the key thing is that the op amp output is a voltage level. Now what simple electric component produces a voltage level? Well, a battery can be a source of voltage. And so, from an electrical perspective, we can think of the output of the op-amp as just a battery, except that this battery does not source a fixed voltage. The voltage that it sources is variable and is dictated by the op-amp equations. To indicate that the output voltage of the op-amp is variable, some folks place an arrow across the battery, but most books and lectures represent the variable voltage source as a circle, as we are now going to show right here. This is the electrical representation of the op-amp that we used extensively in the previous episode to solve all type of op-amp exam problems. The value of the output voltage is of course controlled by the op-amp configurations. For examples, it can be the equation for the voltage follower, the inverting, or the non-inverting configurations. Or it can be a new and different equation for a different kind of configuration, as we saw in some of the new configurations that we analyzed in the previous episode. Now let's see how this electrical representation of the output impacts the current exiting or entering the output of the op-amp. The interesting thing about a voltage source is that they can drive electric current in either direction depending on the voltage polarity. So if the voltage source is producing a positive value for the voltage, then the current it drives will egress from the positive terminal of the voltage source, and it will also be pulling the same amount of current from the ground. Alternatively, if the voltage source is producing a negative voltage, then it will be pulling current into its positive terminal and also pushing the same amount of current into the ground. Now returning back to our inverting amplifier, but now adding the voltage source that represents the electrical behavior of the output, we know from the amplification equation of the amplifier that it inverts the input voltage as it amplifies it. That means that the voltage source that represents the op-amp output will be negative and therefore will be pulling in the required current, in this case I sub F, from the resistor RF and directing it into the ground connection that is inside the op-amp. Which gets us to the question of whether there is any internal resistance associated with the output terminal of the op-amp. The answer lies in the fact that batteries and voltage sources have no resistance, or if they do, it is extremely small and can be considered to be almost zero. And that is why you may have read that op-amps have zero output resistance. They can sink or source current without having to worry about the internal resistance. As we wind down this episode, what have we learned about negative feedback in amplifiers? We explored two essential design concepts that work together to make useful amplifiers out of op-amps. The first concept was negative feedback. That is the process of having a version of the output of the system, which in this case, the output of our amplifier, be subtracted from the input by connecting it back to the negative input of the op-amp. Negative feedback ensures that the system operates in the useful region where the output and input are linearly related. The second design concept had to do with the internal gain of op-amps. We found that we need to keep it extremely high and ideally infinite. This infinite gain served two purposes. First, it forced the subtraction of the negative feedback signal from the input to be extremely small, which then forced the op-amp to operate in the linear region no matter what the value of the input signal was. Secondly, it ensured that the amplification factor of any op-amp amplifier was controlled by the value of the resistors in the feedback network. This enabled the makers of electronic components to use the same op-amp design in a variety of electronic products. So now we have two potential paths ahead of us. If you are a student studying for an upcoming quiz or an exam, you will likely want to proceed to our presentation on how to solve op-amp circuit problems for tests, quizzes, and exams. That is, if you had not seen it previously. Alternatively, if you want to explore how one builds op-amps out of basic electronic components, then you will want to proceed to our next future episode titled How to Build an Op-Amp. All you need for that episode is basic understanding of resistor circuits. We will explain the basics of how transistors work and how you can use them to build an op amp. Thank you, and best wishes to you.